Hey, what's going on, guys? Let's do this problem right here. The question is asking a sphere with the emissivity factor that is 0.42 of radius 25 centimeter is at 27 degrees Celsius. It's placed in a room with a temperature of 2 degrees Celsius. The first question is asking what is the rate of heat entering, heat energy leaving the sphere, and heat energy entering the sphere. What is the net rate of heat energy for the sphere and how long it will take. So let's see how we can find it, but before we do that, let's draw a sample diagram for this question. So we have a sphere right here, right? So we have a sphere with a radius of 25 centimeter, and the next information that's given, this is in 27 degrees Celsius. So the sphere is into 27 degrees Celsius. It's placed in a room temperature with a 2 degrees Celsius. So the surroundings has 2 degrees Celsius. So this the thing that's going to happen is this heat is going to go into the sphere, and the sphere is going to emit 27 degrees Celsius, but the net rate is going to be outside, right? Because sphere has higher temperature, this one has lower temperature, so it will always go from higher to lower. So the net is going to be in this direction. So this is going to be the net heat flow. So let's answer these questions first. The first question is asking what is the rate of heat energy leaving the sphere. So this is the temperature we are going to deal with, leaving the sphere, because sphere has this temperature and this is leaving the sphere. So here the equation to calculate the net question is asking rate of heat energy. So that is given by delta Q by delta T equal to E theta A T power 4. Theta is a constant that's always remains the same. E is emissivity factor that's provided right here, and A is area, T is temperature. So let's look at the first question. We are answering the A part. So here what is going to be the emissivity factor? That is E is equal to 0.42. That's for the sphere. So 0.42 times, this is constant, this is always going to be same value, that is 5.67 times 10 to the power of minus 8. And then we have area. So this is area of a sphere, not a circle, right? This is a sphere. So area of the sphere is given by 4 pi r square. So this is the area of the sphere. We know the radius. We had to convert this one into meter, 25 centimeter, right? So that's going to be 0.25 meter. And if you plug this value in this equation, you will get 0.785. So this gives us 0.785. And that's the one we are going to multiply. 0.785. And the temperature leaving the sphere is going to be 27 degrees Celsius. But we have to convert this one into Kelvin in order to apply in this equation. So 27 plus 273 is going to be equal to 300 Kelvin, right? So that's what we are going to use. So this is going to be 300 power 4. And if you plug all this value, you will get 151.4 watts. So this many joules are transferring per second. So that's what this means. And then let's look at the B question. The B question is asking what is the rate of energy entering the sphere. So the surrounding is 2 degrees Celsius. That's what we're going to enter in the sphere. So 2 degrees Celsius, only the temperature is going to change, right? Temperature is going to be 273 plus 2. 273 plus 2, that's going to be 275. And others are going to say emissivity factor remains the same, and this is constant always same, and the area of the sphere doesn't change, only this value change. So all you have to do is plug this value, delta Q over delta T is equal to E theta A T power 4. So here we are going to have 0.42 multiplied by 5.67 times 10 to the power of minus 8 times 0.785 times 275 power 4. And if you calculate this one, that's going to give you 106.9 watts, right? So the question is asking, what is the net rate of heat energy for the sphere? Net rate of heat energy for the sphere. So net rate, how we can calculate this one? If you notice, this much is leaving, this much is entering, and what's going to happen? All you have to do is, so this is going to be, if it's a leaving mean, that's negative, right? So we can write this one as, so delta, let's calculate delta. We are trying to calculate P right here. So P leaving is negative 151.4 and P entering is plus 106.9, and if you add them together, that's going to give us the net change. So here the net change is going to be, if you add them together, that's going to give you negative 44.5 watts. So that's going to be the answer for the third question, C part. So the answer for the C part is P is equal to net change, that is negative 44.5 watts, right? Now the last question is asking, how long will it take for the sphere to lose 1 million joules of energy? So let's put it as D. So let's trace this one right here. Okay, so now continue this one right here. So the D part is asking, how long will it take for the sphere to lose this much amount of energy? So we calculated per second this much energy is lost. It's negative, it means lost. This much energy is lost. So we have to calculate how long it was going to take to lose this much energy. So we are trying to find the time right here. Power is equal to energy over time. Time is equal to energy over power. We already know the power right here. And we have the energy that is provided. If we divide this one by this one, that's going to give us the time it's going to take to lose this much amount of energy. So let's plug this one. So this is like 1 million, right? 10 to the power 6, 1 million divided by 44.5 watts. So this is joule, this is joules per second. And if you calculate this one, that's going to give you 22,472 seconds. If you want to convert this one into hour, you just have to divide this by 3600, because in 1 hour we have 3600 seconds. So if you divide this one by 22,472 divided by 3600, that's going to give you the hour. And if you calculate hour, that's approximately 6.2 hours. So that's how it's going to take to lose this much amount of energy. And that's how we do this kind of problems. I hope you guys find this video helpful. See you next time.